Clouds reflect solar radiation back into space. They also trap infrared radiation emitted under the clouds. Two competing effects that are the biggest source of uncertainty in predictions of our future climate. The radiation balance depends on many factors, including the three-dimensional structures of clouds throughout the atmosphere, which is not easy to measure on a global scale. ESA's and JAXA's new EarthCare mission was successfully launched on the 28th of May 2024 and will use LiDAR, radar, a multispectral imager and a broadband radiometer to assemble a 3D snapshot of the atmosphere along narrow tracks. However, this strip represents only a small fraction of the atmosphere compared to the 2D imagery acquired every day by satellites in geostationary and low Earth orbit. The 3D Clouds team aims to use machine learning and multiple 2D images to reconstruct the three-dimensional cloud structure beyond the narrow tracks, ultimately providing a robust model of our atmosphere over long timescales to better understand our future climate.
Hi, I'm Joppe, and to know why clouds are so important, let's take a look at this rather scary graph of climate change. One thing that really stands out here are these very high uncertainties. To know why that's important, I'm going to quote Nobel Prize-winning psychologist Daniel Kahneman in saying that climate change is so paralyzing because it is a distant problem requiring us to sacrifice now to avoid uncertain losses later on. And this uncertainty really is a key word here. There's something in the climate models that is clouding our vision. And I kind of gave it away here, but clouds heavily impact the climate and they are a major source of uncertainty. Clouds cool the planet by reflecting sunlight, but they also warm the planet by absorbing heat. And as the climate changes, so will this dynamic, which results in high uncertainties. What is really missing from these climate models are real-time 3D global cloud maps. So, how can we get there? Let's take a look at how we currently measure clouds, and luckily we have satellites for that. And a very good example of this is the recent ESA mission EarthCare, which produces these very detailed vertical cloud profiles. As you can see, however, the profiles are very, very narrow, and that can give us a global coverage about every 25 days, which is already very impressive, but can we do better? Could we look at our other friends in the sky for help? There are dozens of satellites imaging the Earth many times a day. What if they could help? What if we could go from a two-dimensional satellite image to predict the vertical cloud profile? And if we could do that, what if we could use the spatial extent of those images to go towards 3D? That was a focus of our challenge. This is what we have been working on for the past 2 months with this amazing team. And what makes us so uniquely positioned to tackle this is the combined expertise in satellite imagery. We have experts in clouds and how they affect the climate, and we have specialists in artificial intelligence. Stella will now cover more about how we tackled this challenge.
Thank you, Joppe. So, the idea of our challenge is to build a model able to go from satellite imagery to 3D cloud maps. And to accomplish that, we have developed Nephos. But first, let's have a look at what satellite data we have to tackle this challenge and how do we get to this data. On the one hand, we can take advantage of satellites that are in the same track. Here we have a satellite generating cloud profiles, and in front of it we have another satellite delivering 2D images at the same time. The combination of these data sources is really powerful on training AI models. On top of that, and in order to go towards real-time maps, we can take advantage of satellites which are always measuring the same place on Earth, but at very high temporal resolution, every 15 minutes. This could allow us to generate 3D cloud maps in real time and also explore cloud dynamics and evolution. So, how can we leverage this data to train machine learning models? As a first step, we align this diverse data in space and time and create unified 3D representations. This enables the models to learn the relationships between images and the cloud profiles, but also generate 3D outputs. The next step is then to actually train AI models to go from these 2D images to this profile reconstruction in a 3D cube. So let's delve a bit deeper into what our learning strategy looks like. We start by basing ourselves on a state-of-the-art neural network architecture, the so-called UNet, which has been proven to be very powerful on reconstructing 2D images and 3D shapes. And if we have a look on how well it does, we can see that after even 1 hour of training, it's already learning the altitude of clouds and the very vague patterns of whether it's cloudy or not. And after some more extensive training, it's going closer to what we actually want, the real cloud profile measured by the satellite. And now Emiliano will talk about how we further push this state-of-the-art model.
Thank you, Stella. So how do we improve upon this state-of-the-art result? The bottom line is to use more data. Along the satellite tracks, we have satellite imagery and vertical profiles, which can be used to answer the question, if a cloud has a given spatial pattern, what does its vertical profile look like? For this, we have gigabytes of image profile pairs that can be used to train AI models. Off track, we have only satellite images. These could potentially be used to learn more generally about cloud behavior. In this case, we have much more data, in the order of 1,000 times more. So how can we combine the small specialized dataset and the large general purpose dataset in order to get high quality 3D cloud maps? Our NEFOS methodology is a two-step approach where, in a first so-called pre-training step, we use the large dataset of satellite imagery to learn generally about cloud behavior. And in a second so-called fine-tuning step, we use the smaller dataset to specialize the model's knowledge of what a cloud's vertical profile is based on its spatial pattern. In the first pre-training step, using the large dataset, we develop a model that learns general cloud behavior by using the self-supervision trick. This trick involves pairing each image in our large dataset with a masked version of itself. The AI model is then tasked with reconstructing the original image from the masked version. To do so, it is forced to learn deep universal properties of cloud behavior. In the second fine-tuning step, we switch out part of our AI model with the new version specialized in 3D cloud reconstruction and train it with our small dataset. The final AI model uses information learned from the large dataset in yellow and from the small one in blue. As for the results, on the left we see a cloud image, and on the right we see vertical cloud profiles where the top panel shows previous state-of-the-art vertical profile reconstruction. The middle panel, our model's vertical profile reconstruction, and finally, the bottom, the measured vertical profile. We can see that our model recovers a sharper, more accurate reconstruction. Now Lily will talk to you about what our work will enable for the scientific community.
Thank you, Emiliano. So in addition to predicting the actual vertical measurements taken by the satellite, we used our models to directly reconstruct key quantities that scientists are interested in. In this example, a model predicts whether an area is clear sky or cloudy and identifies the cloud type. This enables us to validate our model using vertical measurements of cloud types from satellites as well as ground-based sensors. Here we can see that our model accurately reconstructs high clouds and even correctly detects some clouds that are covered by thin cloud shields. So we've been talking about 3D clouds and so far have been showing two-dimensional vertical profiles of our predictions that are looking better and better. But wait, there's more. While the cloud profiles are these thin vertical slices, our model directly predicts clouds in 3 dimensions. It learned to reconstruct a 3D cube of clouds from satellite images via training on 2D profiles. Here you can see one example of such a 3-dimensional reconstruction from our model. With NEFOS, we can increase the extent of vertical cloud data spatially, a key step towards creating global 3D cloud maps. And not only that, since our model was trained to predict clouds from geostationary satellite images, which are available every 15 minutes, we can make continuous time reconstructions of clouds using a series of satellite images as inputs. We have thereby extended vertical cloud data in both space and time. To summarize, what does NEFIS enable? We built a modular satellite data processing pipeline that can be used for future Earth observation projects. Our model uses global satellite data, which is publicly available near real time. By providing our models and data processing tools to the public, we enable anyone to create 3D cloud maps at any time for anywhere on the globe. Our modular tools, which are trained on previous satellite missions, can easily be adapted to learn from EarthCare's higher quality data once it is available to make even better predictions. So with NEFIS, we provide a 3D cloud reconstruction tool that the community can build upon in the future. This project brings us closer to obtaining 3D real-time cloud data, which will enable scientists to study the behavior of clouds better than ever before, and has the potential to advance climate science and improve climate models. This will make climate projections more accurate and bring the scientific community one step closer towards solving the climate puzzle. Thank you very much.